Topic, it's a big one. The topic is the factor theorem. Last thing we're going to cover. Very important. It leads into a lot of stuff you do next year. So to start things off, like if we were going to, let's just warm up a little bit. If we were going to try to solve this polynomial equation, think back. John, that phone's got to be away, like away. So if we were going to solve this thing, what was our strategy for solving polynomial equations? If you think back 2 units ago, the stuff we were doing in chapter 7, what did we do? What did we do? Well, okay, we don't. But that stuff you guys aren't familiar with yet. I mean, that's okay. We want to split it into factors, don't we? Right? We want to solve by factoring. If we can break this big polynomial up into a product of smaller factors, then we can, by the zero product property, we can just find out when each of those factors is equal to 0 to get our solutions, right? Okay, so how would we have done a 4-term polynomial? What do you think? Split them into groups, right? Okay, but before we do that, let's just make sure, is factoring by grouping? We can test to see if it's going to work by looking at the coefficients. Now look at the coefficients here. The first 2 coefficients in the first group are 1 and 3. The coefficients in the second group are 5 and 15. How do we know that grouping is going to work by looking at the coefficients?
5 times 3 equals 15.
Okay, well, kind of. I mean, that's actually not it. But it's the ratios are the same. If I look at the ratio of the first 2, this is called the ratio test, right? We talked a little bit about this, but we didn't spend a ton of time with it. But it's important because you don't want to waste time trying to factor by grouping if it's not going to work. If the first 2, the ratio of the first 2 coefficients is equal to the ratio of the second 2 coefficients, 1 over 3 is the same thing as 5 over 15, isn't it? Right? So we know it's going to work. It passed the ratio test, so factoring by grouping works. Okay? And remind me, what did we do to factor by grouping with the first group? What did we do? Just good review. Factored out a GCF, which is an x squared. What's left behind? Good, x plus 3. And then the second group, what do we know about the second group? It's got to have the same leftover, same binomial, right? So to make that work, what would I have to factor out? 5, okay. And then we got it, right? Then we know that now we've got our 2 groups. The common factor that I could factor out of each group is x plus 3, right? So I'll pull the x plus 3 out front. And what's left behind? Well, x squared plus 5, right? And that's all it took. Now I've got this thing down to small enough pieces that I can set those factors equal to the small factors, the blue and the red factors, equal to 0 and solve those, and those are easy, right? The whole polynomial was too big. We don't have a way to just get answers to this polynomial. There is no cubic formula, right? But once I break it down into an x plus 3, that's simple. And look, I get a quadratic equation when I set the red factor equal to 0. Those are easy for us now, right? So when I apply the zero product property, I'm just setting my factors equal to 0 and solving. So what's my first solution? -3. Okay, good. And if I set the red factor equal to 0, I get a simple quadratic equation. Now, how would you solve that red quadratic equation? Subtract 5 and square root. Yeah, we can isolate x. I can point to a single x so I can isolate it with inverse operations. Good. Okay, you guys got this. Wow, this is great. Okay, so we subtract 5. We get x squared equals -5. Thank you. Ooh, look at that. Some kind of major award there. Awesome. So last step you told me was to square root both sides. Okay, what do I have to remember by the square root property, if I square root both sides of an equation, what do I always have to include? Plus or minus. There you go. Good. So I get x equals, the square root is telling me plus or minus. Now, what about our other rule? A negative inside a square root becomes, okay, that becomes an I outside. And what's left behind? Square root of 5. Okay, so as we mentioned the other day, 2 days ago, what's the degree of this polynomial that we started with? What's the degree? 3, right. How come? Because it's the highest exponent. Highest exponent. The biggest power of x tells us the degree. So if the degree of the polynomial is 3, we know we're guaranteed to have exactly how many complex solutions? 3, absolutely. So we better find 3, and we did. Negative 3 was one. Positive I times the square root of 5 is another one. Negative I times the square root of 5 is the third one. We got them. Okay, good. All right, so then what happens? Let's try another one. If we tried to do this, solve this polynomial equation, is grouping going to work? Thumbs up or down? Down is right. It's not going to work. Look, if I try that ratio test, I get 1 and 7 are my first two coefficients, and then I get negative 6 and negative 72. Well, that's a problem because 1/7 is not equal to negative 6 over negative 72. So don't waste your time. Grouping won't work. It's just going to fail. It's just going to be a waste of time. Okay, so this is one that we could not solve. Okay, but today we're going to learn a trick, the factor theorem. We're going to learn a trick that, with a small hint, is going to allow us to solve that thing. And next year, what you guys will do is you won't even need the hint. You're going to learn something called the rational root theorem that we just don't have time. And that's really not something you normally cover in Algebra 2. So it's, I wanted to get there, but we didn't. That'll give us a little trick for finding a list of possible zeros that we could try until we find one that works. That'll be next year. Okay. So we know this one doesn't work. We'll move on to something else. Now, to get there, let's shift gears a little bit. Let's go back and just review some concepts. So if I divide 8 by 3, what do I get? I get, how many times does 3 go into 8? 2. With a remainder of what? Whoops, get 2. 2 are 2, right? Okay, which would mean if we wrote that as a mixed number, it's just equal to 2 and how many thirds? 2. Okay. So is 3 a factor of 8? No, it's not. How do you know? It doesn't go into 8 evenly, right? Which means it has a remainder, right? So because it has a remainder, r is equal to 2, the answer is no. What's 8 divided by 4? 2. Yeah. It's equal to 2 with a remainder of what? 0. Aha. Okay. So we would just write our answer. We don't even write a fraction. We just write it as 2, right? Okay, you tell me, is 4 a factor of 8? Yeah. How come? It goes in evenly, which means the remainder has to be 0, right? Okay, that tells us something important. When the remainder is 0, if I do division and the remainder is 0, that means that what I divided by is a factor, right? If the remainder is not 0, it wasn't a factor. Okay, so let's try a couple things here then. Actually, I'm going to skip ahead for a second. So if we look at a picture of this polynomial, okay? If we look at a picture of this polynomial, here's a partial graph of f of x equals x cubed plus 7x squared minus 6x minus 72. Does that look familiar? That's the one we just tried to solve, right? We tried to solve that equation and we couldn't do it because grouping didn't work. But this picture of the graph gives us the clue we need to solve this thing. What do you think is the important clue that that graph gives us? Yeah, look, it gives us an x-intercept. Very important. It tells us right here, it tells us that, what is the number value of that x-intercept? Well, I want the x value. 3. Okay, good. So we know that the coordinates of that x-intercept are 3, 0, right? The y value is 0, okay? That tells us something important, right? That tells us if the x-intercept is 3, then 3 must be a 0 of the function, okay? X-intercepts, this is a really important thing that we mentioned a while ago, but you may have forgotten. Real zeros are always x-intercepts every time. Okay, so that's giving us a 0 of the function. Okay, that's important, right? This is telling us that x equals 3 is a 0 of f of x. Okay, let's back up a little bit and explore, just remind ourselves about what that stuff means. Okay, so if I want to evaluate a function like this, I want to calculate f of 4. How can I do that? I plug 4 in, right? Okay, if I want to find f of 4, I can just plug 4 in for x. That's one way to do it. How can I use my synthetic substitution trick? How can I use synthetic division to substitute a value into a function? Do you remember how that works? Okay, there's a way to do this, right? This is one of the tricks we learned back in Unit 7, okay? Remember what we can do. The number that we're plugging into the function goes where in my synthetic bracket? Okay, good. That's the outside number, isn't it? So if I plug 4 in, 4 is the number that's going to go out there. What numbers do I put in my top row? Okay, there you go. Good. I put the coefficients. So 1, 7, -6, and -72. Now let's just do the process. And that's my remainder box, right? Okay, if I do the process here, remind me how to do synthetic division again. Good. I drop the 1, multiply by the outside number, then is it add or subtract? Add. Yeah, I do the opposite of long division. I add with synthetic. 7 plus 4 is 11 times 4, 44, plus 6 is what? -38? Or sorry, 38. And then 4 times 38, yikes. Well, 4 times 40 would be 160 minus 8, so 152. Add those up. What's -72 plus 152? What is it? 80, right? Okay. And you could do, I mean, I don't want to waste time like doing calculator. You guys could just plug these numbers into a calculator, right? That's not a big deal. Okay, so I want to know then, what is f of 4 equal to? Can you tell me? It's 80. Yeah, exactly. That's the trick with synthetic substitution. When I plug the input value out in front of this synthetic bracket, the number I get in the remainder box is the value of the function. Okay? So if I look at this graph of this function again, if I go out to 4, the value of the function right there, if I look at that ordered pair, when x equals 4, y equals 80, which makes sense because look, the y-axis, we're going by big chunks there, aren't we? That's 125 right there. So sure enough, like I'm up quite a bit. I'm up at 80. Okay, make sense? Okay. Okay, what about, let's try this one more time. What about f of 3? Okay, I'm going to do the same thing here. So I'm going to make a synthetic bracket. What goes out front? 3. Same process as before. We can just copy, right? The coefficients are the same. They're just 1, 7, -6, -72. Can anybody predict from the graph what the output is, what's going to be in the remainder box? Yeah. How come? That's what it is. That's the value of the function, right? It's an x-intercept, which means it's a 0 of the function. Like sometimes when we say these words, don't let them be mysterious. If I'm talking about the 0 of a function, what does that mean? Like if I have a number that's a 0 of a function, what does it do to the function? I mean, kind of, in a way of thinking, maybe. What happens if 2 is a 0 of some function, then what happens? What's the value of the function when I plug 2 in? 0. That's the whole point, right? The job of a 0 of something is to make it 0, right? So when we solved these equations here previously, right, we did some work back here. We used grouping to factor our polynomial. Used the 0. It just means that the product of the factors is equal to 0 at the zeros of the factors. We just needed to find the zeros of the blue factor and the red factor, right? And we found them. -3 was the 0 of the blue factor because -3 is the number that makes that factor equal 0, right? The two numbers that made the red factor equal 0 were plus or minus I times the square root of 5. So those were the zeros, okay? Here's a tricky question. How many, if I were to graph this function, how many x-intercepts would it have? 1 is right. Even though it has 3 zeros, how come there's only 1 x-intercept? Okay, because look at these. Are these real zeros? No. Only the real zeros correspond to x-intercepts. Imaginary zeros do not, right? So we only get 1 real 0, so that one only has 1 x-intercept, okay? All right, so then let's go back to our, so you guys are right. You predicted correctly. The output is going to be 0. Let's just show that that happens. We'll prove it, exactly. Okay, so what happens here? If I bring the 1 down, 1 times 3 is 3, plus 7 is 10, times 3 is plus -6. 24 times 3 is, oh, what do you know? What do you know? We get 0 for our remainder box, which tells me that the value of the function is 0. Sure enough, right? It worked, okay? This is really valuable to us, this trick. This is what we called the remainder theorem, right? What is it? Actually, I'll start here. This is what we called synthetic substitution, first of all, okay? Right, synthetic division just becomes synthetic substitution or synthetic evaluation. But that comes from the polynomial remainder theorem, okay? Because if we divide some polynomial f of x by x minus k, which is what we did, right? That's effectively what we did here, right? We divided, you guys told, oh no, we didn't. Hang on. No, we didn't. Sorry. No, we're good. We're good. I want to go back to here, okay? We plugged 3 into this synthetic bracket and used synthetic substitution. But this is also exactly what it would look like if we did synthetic division, right? Synthetic division means that we would have been dividing our original polynomial, which was x squared plus x cubed plus 7x squared minus 6x minus 72, right? That was our original polynomial. If we divide that by what? What did we divide by? 3. Not 3. We don't divide by a number. With synthetic division, we're dividing by a factor that has a variable in it. What did we divide by? A 3 out front means what was on the bottom? No. Come on now. No. Here, I'm going to give you a problem here. You guys know this. I know you know this. I'm going to jog your memory. Okay, so how would you do this? Remind me. How would I'll pick an easy one. What if we did x squared minus x minus 3 divided by x minus 2? How would I do that synthetically? Okay, so what are my coefficients? Okay, there you go. So the number that goes out front, exactly, the number that goes out front would have been what? Would have been 2. Exactly, it would have been 2, right? And the coefficients would have been 1, -1, -3, right? Okay, so then when we did this process, yeah, look at that, right? This would have been the same thing as saying dividing by x minus 3, right? And what would the answer have been? Well, not 0. What did that stuff tell us? Ah. Okay, so this is the remainder. So that's the, well, what do you call that? Constant. That's the coefficient of x. That's the coefficient of x squared, right? So the answer would have been x squared plus 10x plus 24. You guys were used to doing this. Whatever the denominator was, and we can use synthetic division here, and we don't have to use long division. How come? What's unique about the bottom? It's important. Okay, there's no exponent. X is to the first power, and the coefficient of x is 1, right? As long as the bottom looks like x plus a number or x minus a number, remember, those were the conditions we had to meet to use synthetic division, right? And you guys knew this. You told me you could have done this in your sleep, about a month ago, right? You would have told me to build the synthetic bracket with those coefficients, and you told me the number out front is +3. I know you would have, okay, right? So then what's that tell us here then? So if we're dividing by x minus k, what's the number that goes out? K is just a number. What's the number that would go out in front of the synthetic bracket here? K, right? It's going to be the opposite of that sign. So if x minus k is a factor, what should the remainder be? When I run that number k through synthetically, what would have to be in the remainder box if this is a factor? It'd have to be 0. If it's not a factor, I wouldn't get 0, right? What the remainder theorem tells us is that whatever I get in the remainder box, that's going to be the value of the function when I plug k in. So this is just telling us that putting a k out in front could either be division if I'm doing synthetic division, or it could be synthetic substitution if I'm just plugging the value k into the function, right? We just did that. We did it originally. We did this to figure out what f of 3 was. So we put the 3 out front. But we could have also just been doing this. We also could have been dividing our polynomial by x minus 3. I still put the same number out front. Those two things mean the same process, don't they? Synthetic division does two things for us there. Okay, so why is that so useful? Here's why it's important. If k is a 0 of the function, then that means I'm getting a 0 in the remainder box. And what's that tell you about x minus k? If I get a 0 in the remainder box, plugging the number k in front of this synthetic bracket is either plugging it in to use substitution or doing division. But if the remainder is 0, what happens when I do the division? Is x minus k a factor or not if I get a remainder of 0? You guys told me that stuff. You guys told me that stuff a little bit ago. You told me 8/4 equaled 2, so 4 was a factor of 8 because the remainder was 0, right? 3 is not a factor of 8 because the remainder was not 0. So if the remainder is 0, that's what we would get. That means that k would be a 0, right? That's what it means to be a 0. It causes a remainder of 0. So if k is a 0, that's another way of just saying, that's another way of saying r equals 0, right? There's no remainder. Doesn't that mean that x minus k then has to be a factor, right? That's huge. That's really valuable to us. So it tells us that these two statements always go together. If we know that if k is a 0 of f of x, that guarantees that x minus k is a factor of f of x. And those two things always mean the same thing. They always go together. So for example, if negative 3 is a 0, not a factor, if negative 3 is a 0 of some function f of x, what's the factor that has to go with that? No, the factor would have to have an x in it, right? What's our rule? If k is a number, if k is a 0, then x minus k is a factor. Okay, now apply that to this specific example. Negative 3 is a 0, so what's a factor? Good, x minus negative 3, right? I just am going to subtract this 0 from x to build the factor. Everybody get that? That's all I do. If the number k is a 0, then subtract that from x to build the factor that goes with it. Give me thumbs on that. Does that make sense? Okay. So the factor then would just be x minus negative 3, which we would turn into x plus 3, right? So x plus 3 would be the factor. Okay, negative, if x minus 5 is a factor, I want you to tell me blank is the 0. So the 0 is just going to be a number, right? The 0 is the number I plug in to get a remainder of 0. What's it going to be? 5. Yeah, right? Has to be by our little pattern here. X minus 5 is a factor, then the thing I'm subtracting from x is the 0. It's 5. Okay, let's try a couple more. I know these are, come on, go away. Oh, whoops. Then 5 is the factor. Okay, let's try a couple more. If I have some random polynomial, if I know that negative, let's do that, x plus 9 is a factor of f of x, then that tells me that blank is a 0. What? Negative 9. Exactly. Perfect. Okay. One more. I don't want to do that one. I don't want to do square root. That's bad. I don't really need to do that. X minus. I'll do a fraction though. What's the factor? X plus 3 halves. Exactly. X minus negative 3 halves, which is x plus 3 halves. You got it. Okay, that's the factor theorem. That's the factor theorem. Okay, so where this is so useful to us then would be, we've already done the work here to solve this, but you have to figure out why. Okay, so we couldn't solve this equation before, but now we can. It gave us a hint. We can see that x equals 3 is an x-intercept, which means that 3 is a real 0 of the function, right? Okay, so let's write that down. We know x equals 3 is a 0 of f of x. So what's the factor? X, not minus 3, it's, but a factor has to have a variable in it. X minus 3, right? The factor has to have the variable. The 0 is just a number, but the factor is x minus the 0, right? So x minus 3 is a factor. Okay, so if I divide my polynomial by x minus 3, what's the remainder guaranteed to be? 0. Okay, let's do that. Okay. This is going to look real familiar, right? If I divide my polynomial 1, 7, negative 6, negative 72 by x minus 3, that means I'm putting a 3 out front. Agreed? And because 3 is a 0, we know we're going to get 0 for a remainder. We already did this, right? We already did this one. We did this one where? Right there. Exactly, right there. And what did we get? 1, 10, and 24, right? Okay. So we already know what the outcome is going to be. We get 1, 10, and 24. Well, didn't that just mean that when we divided x cubed plus 7x squared minus 6x minus 72, when I divided that by x minus 3, the answer was that, which you already told me was x squared plus 10x plus 24, right? Agreed? Okay. So then really what we just did is we just found that two factors of our original polynomial are x minus 3 and that quadratic polynomial, that green one, right? How do I get there? Well, if I cleared the fractions, we don't have to do this, but if I cleared the fractions by multiplying both sides through by x minus 3, when I distribute to this term, it's just going to cancel that denominator, right? And what do we get? X squared plus x cubed. I keep doing that. Plus 7x squared minus 6x minus 72 factors into x minus 3 times x squared plus 10x plus 24, right? And we're trying to find out when that whole thing is equal to 0. Well, look, we did it. We factored it far enough so we can use the zero product property now, right? That was too big, but when I break it into these factors, now I can set each of those equal to 0 and solve. Either x minus 3 equals 0 or x squared plus 10x plus 24 equals 0. Well, what's the solution that goes with that one? 3. We already knew that one, right? That was our clue. That was the freebie that they gave us up here in the picture. That was a solution because it was the x-intercept. How would I find the other two? That's a quadratic equation. How would I solve that quadratic equation? Yeah, I could find magic numbers, couldn't I? Otherwise I could always use quadratic formula, but magic numbers exist here that make this one easy. Yeah, numbers that multiply to positive 24 and add to 10 are positive 6 and positive 4. So what are my other two solutions then? There you go. Negative 6 and negative 4. How about that? Okay, let's do one more of these together and then I'm going to send you to the boards. So let's start one of these from the beginning and let's see if we can do this one as simply as possible. Now we've talked about this a ton. Now can we just make this kind of straightforward and simple? So we want to solve this equation. F of x equals 0. They tell us something really important here. They tell us that 2 is a 0. Right? Okay, so what's that mean as a factor? Well, x minus 2 is a factor. Good. Okay, so then all I would have to do if I want to find, I have one solution. If I want to find the other ones, I could just use synthetic division to reduce this big cubic polynomial down to what's left over when I divide it by x minus 2. And that's going to give me my other solutions, right? Okay, so what number goes out front? 2, because that's my 0. What numbers go in the top row? 1, 2, -5, -6. What number is guaranteed to be in the remainder box? 0. How come? Because it's a 0, exactly. Because 2 is a 0 of the function, so it's going to have to give an output value of 0. Okay, if I do the math here, I just drop the 1 down. 1 times 2 is 2, plus 2 is 4, 2 times 4 is 8, plus -5 is 3, 2 times 3 is 6, plus -6 is 0. Okay, so now how am I going to find the other two solutions? I know one of them. I know x is 2. How do I find the other two? Yeah, I'm just going to set that equal to 0 and solve, because that's what's left behind if I divide my original polynomial by x minus 2, right? Okay, so then we just get x squared plus 4x plus 3 equals 0. And that one factors, doesn't it? X plus 3 times x plus 1 equals 0. So what are my solutions? So let's capture all my solutions then. How many total should I get if it's cubic? Okay, what was the one that we knew right away? 2. Okay, we knew this one right away. What are the other two? Right? Try this. Go to the boards and try that. There's one for you.
Hey Phil, how you doing, buddy? So basically what we do here, take -1, and then we set up our little equation. So we do like this.
Kind of talk about it. We'll finish it up on Tuesday. So what's going on here then? They want us to, this time it's different. This time instead of finding the solutions, we just want to find the factors. That's okay. Factors and zeros go together, right? So finding, it's really no big deal. Finding factors is the same thing as finding zeros. Okay, the thing that's different about this is, oh man, let me do one thing here. Darn it, I want to do that. There we go. Okay, so they tell us that k is a 0, so -2 is a 0. What does it mean that the multiplicity is 2? Well, no, it just means how many times does that how many times is -2 a 0? Twice, right? So what's the factor that goes with this? Okay, good. But because the multiplicity is 2, it means that that factor is squared. It shows up twice, okay? So how many times should I be able to plug that number in synthetically and get 0 in the remainder box? 2 times, because the multiplicity is 2. It counts as 2 separate solutions because it happens twice. So when we say that this polynomial is 4th degree and it has to have 4 solutions, well, the fact that this has a multiplicity of 2 means that this one counts for 2 of those 4. So how many other ones should we expect to find? 2, right? And so we could just do this. And we're not going to probably finish this, but I could plug this polynomial in. So I get 1, 3, -42, -172, -168. I'm going to plug -2 out front. And what's guaranteed to be in the remainder box? Yeah, guaranteed, because it's a 0. Okay, and so if we do that, maybe we can get through this. If we do this real fast, I bring the 1 down. 1 times negative 2 is negative 2 plus 3 is 1. Negative 2, negative 44. 88 gives me negative 84, which gives me positive 168, which gives me 0. Okay, so it worked once. But the multiplicity is 2, so what can I do? Go again. I can take this result and use synthetic division again. Because the multiplicity is 2, I'm guaranteed to get another 0 there. Okay, and so if I go through this process, I'm going to plug negative 2 in again, right? Because the multiplicity is 2. Oh, darn it. Uh-oh.
Maybe just do the same thing over again.
Right. And then, oh man, almost made it. Okay, we'll wrap this up Tuesday. You got to start the assignment. This is it. You think you get the idea?
Yeah.
All right.